All right, here we go, 1.5. The last section in chapter 1 before we start getting into the really good stuff known as the derivatives. This is like the last little step in building the foundation for our house of calculus. Continuity continued, and the IVT, okay? There's a dearth of vowels in IVT, but that's an acronym. The word of the day is yclept. And like Skurhawk, there is also a dearth of vowels in the words, okay? So anyway, we're going to talk about continuity in 1.5 on an interval, whereas previously we've talked about it at a single point. And by a point, we mean at an x value, okay? But it could also be a coordinate, right? So we're talking about an x value. So to review the three-step definition of continuity. Oh, by the way, just real quickly, obviously, intuitively, we would call this a continuous function, right? I drew it, it's pretty. And right now our intuition of continuity from left to right is, can you draw it from left to right without lifting your pen or pencil, right? If you can do it, it's continuous. That's a real basic intuitive understanding of what a continuous function is. This, on the other hand, would be a non-continuous function. As you draw it from left to right, we've got a jump, we've got a vertical asymptote, we could even possibly have a hole somewhere, or an oscillation discontinuity. It's broken up, it's jagged. You have to lift your pen or pencil. So that's what we're going to explore in this section. How can we talk about or qualify mathematically continuity on an interval from left to right? That's something more rigorous that we can actually, put our finger on. Well, we got to review continuity at a point, and we already just did that with the test, right? Road, bridge, road. Limit from the left of C, f of C, limit from the right of C. Calculate them all. If they're all the same, all three of them, functions continuous at a point. So example 1, I think we could benefit from this. This is just kind of review. This is like what we just did on the test. Determine the values at which this function is continuous, and then find the end behavior limit. So first thing you want to do if you're talking about the continuity of a piecewise function, and you're not given like directions here. It's a project. You have to do it on your own. Look at the pieces first. The pieces are 1 over x plus 3, 2x plus 5, which is a line, x squared is a parabola, and the square root of x, which is parent function. So the two polynomials in the middle are continuous everywhere. The function on the bottom, the square root of x, it's continuous for all values greater than 0, right? Just to review, the square root of x looks like this. It starts at the origin, and it looks like that. So it's continuous over its entire domain. Once it gets started, it ain't stopping. It doesn't live to the left of 0, though. But look at the top piece, 1 over x plus 3. Is that one continuous everywhere if we just looked at that one by itself? Nope. It has a vertical asymptote where? At -3, okay? Let's just write that down. A vertical asymptote at x equals -3, an infinite, non-removable discontinuity. Now, it may or may not even come into play. That's what piecewise functions are all about. Where are they defined? Well, this piecewise function says, hey, use that piece everywhere to the left of -2. Is -3 to the left of -2? It is. So we will see that vertical asymptote. So we know right away we already found one place where that function is not continuous. Now let's look at the bottom piece, the square root of x. It only lives from 0 and to the right. We're defining that to be the graph everywhere to the right of 4. Is 4 greater than 0? Yeah, so once we start at 4, it's going to be continuous everywhere. Hey, see ya. Adios. Yeah. Is it time to go? Oh, he has dentist appointment. Okay, that's cool. So this piece is continuous everywhere. This piece, so that leaves only a couple of places now to check, right? In the relay races in the Olympics, I think it was Japan, right? Did you see how, I don't know if it was the 4x100 or whatever, but they passed the baton and it was like a meme and it was like bouncing around that second guy and it never hit the ground, but it was like, wow, and then he caught it, right? So we need to check the points of exchange where it changes from one graph to the other. Where does that happen? -2, 2, and 4. Yeah, -2, 2, and 4. Those are the x values where it changes. We need to check those individually ourselves, right? Because it could be a hole, it could be a jump, or it could be continuous. Now, if we're going to do, let's do it the correct way one time with the right notation, and then we'll just do it intuitively. Let's check it too. So here's what we could do. At x equals -2, colon. When you do that, you're kind of like labeling your work, right? My driver's instructor used to say, signal your intention, right? Use your blinker. That's what we're doing here. We're putting our blinker on to let everybody know, hey, we're going to analyze at x equals -2. Now, underneath there, off to the right, we'll say, what's the limit as x goes to -2 from the left of f? What's f of -2? And what's the limit as x goes to -2 from the right of f? Now, if you don't want to put f there, you don't have to. If you would rather put the actual pieces, the variable pieces, you can. Let's see what that would look like. Or you could do both. -2 from the left, that's less than -2. That's 1 over x plus 3. Now, if you want to draw vertical lines, you can as well. I don't know if that helps you stay organized. F of -2, that's the second piece, right? If you plug in a -2, you get 5 minus 4, which is 1. And then the limit from the right, again, you don't have to do this, but from the right of -2, it's going to be the function 2x plus 5. And I need parentheses around 2x plus 5 because it's more than one term. Now, you only need one of these. You only need one of these. Same thing on the far right. But it's okay to have both. If you do have both, remember, though, make sure you have two limits. Don't put the limit as x goes to -2 of f of x, and then right next to it, put 1 over x plus 3. Bless you. Now we can use direct substitution. Yeah? If I plug in a -2, 3 minus 2 is 1. 1 divided by 1 is 1. And over here, I know I'm going to also get 1. So now if we had to justify, we would say since or because 1 equals 1 equals 1, comma, f is continuous at x equals -2. So that was a really good baton exchange. One guy was standing right where the other guy was standing when he let it off and passed it on. All right. So that would be the notation if it said, like it would say, discuss the continuity at -2 using the 3-step definition. Let's do the other two just in our heads intuitively. So let's look at the limit from the left of 2 now. Okay. From the left of 2, that's the which piece? The second from the top, right? Because it's x is less than 2. You get 2 times 2 is 4. 4 plus 2, 4 plus 5 is 9. All right, so that one goes up to the point 29 with an open circle. And then look right below there, it's x squared. And that is greater than or equal to, right? You can read that from the inside out. Instead of 2 is less than or equal to x, which is less than 4, you could say x is greater than or equal to 2. So from the right of 2 and at 2, it's 2 squared, which is 4. Does 4 equal 9? No. So we know that's not a good baton exchange. It's like, here, catch, and they throw it. So what type of discontinuity is that? It's a jump. So F has a jump discontinuity at x equals 2, all right? Because 4 doesn't equal 9. And then the last one, let's check 4. From the left of 4, that's less than, we get 16, right? 4 squared. From the right of 4, we get the square root of 4, which is 2. 2 times 8 is 16. The limit from the left is 16. The limit from the right is 16. Is the function continuous at 4? Right. There's no bridge. That's not included. The limit exists, right? The limit exists. If the limit from the left equals the limit from the right, then the limit exists. The roads are lining up, but there's no equal sign. It's just less than 4 and greater than 4. Neither one of those includes 4. So by definition, this function has a hole at 4, 16. Okay. If you wanted to fix it, just add a little equal sign to either one of these, and now it's continuous. So you got to look very carefully. So that is reviewing continuity at a point. Tomorrow, we'll get into continuity on an interval, and it's a pretty short section. So we'll probably be able to finish tomorrow. All right. So be working on the worksheet if you want. You probably don't have enough information to do it, but for now, make sure you really understand the test and what you got wrong and why you got it wrong. Okay. All right. Y'all have a great, fantastic day. What was that, Landon?